Okay, hi everybody. I'm Steve Saar, and I'll be talking about all the problems magnetic fields, or only some of the problems magnetic fields give us to our RVs, on top of all the things we already know about. There are many well-known and unloved sources of RV jitter: star spots, plages, magnetic network, granulation, meridional flows more recently, and also there's other flows that I'm working on, the penumbral and mote flows and active region inflows. But actually, almost all of these, except for the granulation and meridional flow, you can blame on magnetic fields. It's all magnetic fields interacting with stellar plasmas and either suppressing convection and suppressing heat transport. So magnetic fields already are causing us all these problems. What about the fields themselves operating on line profiles? Because we certainly know that happens. Now, this has first been investigated by Ansgar Reiners and collaborators in 2013, and I highly recommend people have a look at that paper if you're interested. There's sort of two main things going on here. There's the anomalous Zeeman effect, which is that not all lines are simple triplets, and magnetic intensification, which comes about because magnetic fields, the splitting of lines can basically gives you more wavelength space that you can absorb out of, and that can increase the equivalent width of your local line in the magnetic region. The Zeeman effect broadens lines in active regions in complex and line-dependent ways, depending on the particular Zeeman splitting pattern that the line has. Magnetic fields have a distinct center-to-limb effect. The line is basically, there's two parts of the split line. There's the circularly polarized and linearly polarized components, and they have different center-to-limb effects. And as I already mentioned, the equivalent width can change in stronger lines. And all these things, you can imagine all these things working on your local magnetic line profile that's now traveling in a plage across the disk of your star. This is going to do something. And the question is, well, how important is it? And how much does this alter the apparent radial velocity? Again, first work, you can have a look at Ansgar's paper for a good start. This is sort of kind of a further investigation of some of the details. Okay, so as I alluded to, the presence of flux affects line broadening. It's dependent on the magnetic sensitivity, the Landé G value, and on the strength and number of Zeeman components, the wavelengths of the line strength, the magnetic field itself, and the fraction of the surface that is covered by fields. Here's an example from a paper by Chukov, 2020. Four quite similar iron lines, similar wavelengths. One of them has a Landé G 0, so no magnetic effect at all, that's upper left. And then the other three all have pretty similar G effective values, but the anomalous patterns are quite different. And that's indicated at top there. The linearly polarized pi components are indicated by the black lines and the relative strength and splittings, and the circularly polarized sigma components are shown by the red and blue. And when you model the lines under different magnetic field strengths, you can see that even though the G effective of a line, which is often used as a diagnostic for how sensitive the line is, it's basically the intensity weighted average of the sigma components. But as you see, even though these three lines have quite similar G effective, their actual effect on the line profile is quite a bit different. The upper right line, 5497, is quite a bit more effective, say, than the lower left line. So that is the anomalous effect, and how the relative splitting number and spacing can really change things from line to line. So even just scaling by, although for simple triplets, you have a fairly nice relation showing the lower left, where the radial velocity is proportional to the area and the G effective lambda and magnetic field strengths squared. It definitely gets more complicated when you have a more complicated Zeeman splitting. So I decided to investigate this a bit more, using a very simple Milne Eddington radiative transfer, including magneto-optical effects, Faraday rotation. In this case, I'm just doing simple triplet lines and looking at the effect of the line strength for average Hart's north line parameters. So that gives an average wavelength of about 5,000 angstroms, average effective longitude of 1.2. I used a 1% area plage and a 1400 Gauss field, and computed what the RVs appeared to be from Gaussian fits of the resulting line profile. And this is what you get. The weakest lines, basically the line strength is gives the weakest lines give the relatively strongest effect, and then as the lines become stronger, the curve decreases in amplitude and actually reverses sign at some point. So your strongest and the weaker lines, and decreases with line strength. Basically, as the lines get more optically thick, it's harder to increase the local radial velocity. And the lines, the effect changes sign in the strongest lines, probably because as the lines start to become optically thick, as they saturate and broaden, the effects spread out over more wavelength, and thus are somewhat diluted. And you also don't get as much effect in the core where everything is very thick. And note, however, that these curves will be different for non-triplets, and we'll be going into that next. So I've alluded to some of this already. You know, why are those curves so complicated? Part of it is just the fact that you've got changing Zeeman patterns, relative strengths of your Zeeman components as you move across the disk. Off at the right, recall that at the limb you've got the linear polarized component and two shift and the split sigma components for a simple triplet. Whereas at disk center, you lose the linear polarization component in the middle. So basically, you have imagine this moving through a profile. It won't be as extreme because the magnetic field will not be as split as shown here. But this is just for so easier visualization. But you're basically starting with the top at the limb and shifting towards the bottom at disk center. And then of course, the equivalent width increases can increase in for stronger lines. The sigma and pi components can be split in complicated ways. and the effect can change as your particular area moves from the optically thin wings of the line to the thick core. So what happens in a typical, we're just on individual lines so far. What happens when you make an RV observation of many different lines? Here I've computed the line strength distribution for a subset of very unblended lines that was picked by Miklos et al. In 2020, with about 735 very clean lines from the Hudson Rivers. The line strength distribution is shown at the lower left. You can see it peaks at sort of moderate strength lines. There's not as many very weak ones and not so many very strong. And then more as a comparison, on the right is the full depth distribution for the HARPS G2 and K5 masks. The K5 star is given by the thin distribution. The G2 star is given by the heavy one. And the Miklos sample that I was just talking about is given by the dashed distribution, which kind of trims the very weakest and strongest lines to an extent. Okay. So what you can do is in wavelength bins, compute distributions of line strengths, and then use the fold that through the radial velocity curves that I showed you before, scaled to the appropriate wavelength and such, and produce a combined average effect that you'd expect from the spectrum. And when you do that for the Miklos set, you get the heavy dashed curve in the middle, which has an RV amplitude of 11 meters per second for a 1% plot. So that's sort of what you might expect for, sorry? This is about 3 times what Ansgar got from a somewhat similar calculation in 2013. But they also did some things a bit differently. They computed the radial velocity for all the lines that are stronger than about 2% in the spectrum, including lots of blends, which are not generally used for RV calculations. Generally, mostly unblended lines we use. They also, however, computed full Zeeman patterns, and this experiment right here is just the simple triplets. So there's a couple of things that are different that might explain differences. So the next thing we can look at is, okay, what about anomalous Zeeman patterns, and how do different patterns affect the same lines? Okay. So here I've picked 3 transitions given in the table over there. They all have very similar Landigi effectives. And then I've also computed the standard deviation of the pi component distribution, the standard deviation of the sigma component distribution. That's the x pi and the x sigma. And then the y1 parameter, which is the skewness of the sigma distribution. And use particular notation and the calculation as courtesy of Landigi paper back in 1952 or so. These are all sort of artificial lines with these transitions that were all computed with the same line strength and at the same wavelengths, and same magnetic field strength and all that kind of thing. And the somewhat scary thing is that you get the following RV curves in the lower right. So in spite of all these lines at least if you look at G effective, being similarly magnetic, they can have some pretty wildly different behaviors in terms of their RV signal. And we can look at them one by one. For context, there's the top line, which is just a simple triplet. The Zeeman pattern is shown at lower left, where the intensity is plotted against the G of the particular component. Pi linear polarized components are dashed, and solid components are the sigma circular polarized component. And for this particular, for the simplest case, the RV amplitude is 11 meters per second, and it's a simple triplet. So the strongest sigma component is at the G of 1.5, and the strongest pi is at line center at G of 0. Okay, well, let's look at another with a different pattern. Okay. Here is, this one has a slightly lower G effective, but it's pretty close. It has a symmetric narrow sigma distribution and a narrow pi distribution with a positive skew. So actually, that's a negative. Negative skew actually. So here you have quite a bit larger signal. That's the in the lower right. That's as indicated by the orange arrow. That's an amplitude of 54 meters per second. The strongest sigma component here, and actually an average of two of them, is right around 1.5. And the strongest pi component is shifted slightly at 0.5. Okay, the next line has the following splitting pattern. The strongest sigma component is at 1, and the strongest non-zero G pi component is also at 1. So that's less than either of the previous cases. And it was a fairly significant skewness, positive skewness to the sigma component distribution. So this one has the lowest RV amplitude of all. It's only 7 meters per second. The next one has the following distribution. It has a narrow positive skewed sigma distribution and a narrow pi distribution, unlike the previous that had quite broad distributions of both of them. A little different here is that the strongest sigma here is at 1.33, G of 1.33, and the strongest pi that isn't at 0 is just slightly shifted at 4.1. And this one has a somewhat larger amplitude of RV amplitude, 28 meters per second. Again, indicated in the lower right with the orange arrow. And the one with the biggest signal of all is the bottom line. It has the following distribution, has the strongest sigma component of G of 2, and the strongest non-zero G pi component at G of 1. It has a broad sigma distribution with a negative skew and a broad pi distribution, and its RV amplitude is 65 meters per second. Okay. So here are some patterns that seem to be emerging, and I can go back and point them out a bit more. Is that as expected, the RV, as due to magnetic fields themselves, varies with lambda G and with line strength, but also with the position of the strongest sigma and pi components. Those seem to be it seems to be a fairly important factor here. The higher the G value is for the sigma and pi components, the more RV more RV you get out. And the breadth and skewness of the sigma and pi components is also seems to be important. Negative skewed ones, in other words, the lines with the strongest component at the highest G's. In other words, the furthest out from line center is, as one might expect, gives a larger RV signal. So all lines are definitely not equivalent. Neglecting the Zeeman patterns can lead to quite a bit of excess RV scattered. They're buried in your signal. Depth weighting when you make a CCF is going to bias you in velocity towards the signals of the stronger lines, which tend to have actually lower delta RVs due to magnetic field, this magnetic field effect. Now, in some ways, that's good because it's sort of dampening out the magnetic field effect. But if you want to correct for the magnetic field effect and remove it entirely, or at least try to, you need to be able to see that signal. So in that case, it's kind of hurting your ability to detect the signal. And I think this is really kind of suggesting that it's important that lines should be treated individually, or perhaps in groups of similar scalable Zeeman patterns. And if you're using pattern groups, then a good question is how best to define your group and how to scale it. I mean, perhaps we need a new something equivalent to the effective lambda G for that kind of a scaling approach. And that's really about it. I know that there's a lot of detail in there, so I can go back and we can discuss cases and things, but that's really the gist of it. So,
very good. Thank you, Steve. Yeah, some nice clapping hands emojis. So people are clearly excited and I imagine somewhat terrified by these results. If folks have questions, please raise your hand via Zoom. Drake, I see your hand waving frantically in the video, so we'll start with you. Other folks, please feel free to raise your hand using the button, and I will call on you after we hear from Drake.
Steve, as scary as this is, I'm thinking maybe it's the real situation is even scarier, because I think you've talked about the distribution of the pi and sigma components, but you're adopting that the individual pi and sigma components are independent, their profiles are independent of viewing angle. Whereas in the real sun, we know in the infrared lines, in the 12 micron magnesium lines, the pi components are more narrow when you look across the field lines due to suppression of motion across the field lines. So could that make this scarier if the profiles of those components change?
You're right. I assumed that the profiles of the pi's and sigmas were basically the same. And I had forgotten about that. 12 micron result.
Yeah, the real sun is really nasty.
Yeah. So yeah, that would cause yet another effect.
Okay, other questions? Looking for hands in the participants list, or feel free to unmute and ask. Oh, Heather, go right ahead. I think you're muted at the moment.
Can't hear you.
Thanks, Steve. What motivated the choice of 1400 Gauss for your plage? Is that seems like it might be a fairly magnetic plage, but I'm used to simulation land, so I'm not sure how that works when we're talking on measured on the sun.
Oh, well, that's based on some work by some of Sami Solanki's collaborators, where they're looking at the actual local field strength. That's diluted by whatever the filling factor in the plage is, because there's some non-magnetic in there too. And they find a fairly narrow distribution around 1400 Gauss or so. So I was just adopting that. There's also, of course, this sort of ubiquitous, very low level magnetic field that's on the sun. That's like around 100 Gauss or a little bit less. And that's another business, but I hadn't simulated that.
Okay, thanks.
Are there questions, comments, concerns from the audience? I'm curious, Steve, maybe you can speak a bit more on this. So one of your conclusions was that maybe we should be trying to group these lines when doing RV measurements by this type of behavior. Can you speak a little bit more about what that effort might look like, and if it's a feasible thing to try and implement with our current level of knowledge, or is there a lot more work that would need to be done before we could define those bins in a effective way?
Well, Landi de Glennicente defined some subclasses. I've kind of indicated that with the type column there, and I went with that, and they're basically based on how the sigma components are distributed. But that seems to be, now looking at these results, that seems to be only one way to potentially parse it, and I'm not sure that that's the best necessarily, but that's just the one that was available, and I went with it. He based the categorization on the skewness, the relative skewness, that whether zero, positive, or negative on the sigma component. And there certainly is a factor. I mean, that does factor in the negative skewed value. In fact, that's the one we're looking at right here. Has the strongest signal of all. And that's because, or at least I think it's because you've got this, even though G effective is 1.5, the strongest sigma component is out here at G of 2. And I suspect that when you go to, do a Gaussian fit, or however you want to measure the RV for a particular line, it's going to key in on where the deformation of the line is strongest. And you've got the sigma component, the strongest sigma component at G of 2, the strongest pi component that is split at G of 1, and that's probably the highest combination of those two among all 5 of these lines.
Other questions for Steve?
So it's still a work in progress as to exactly what the best.
Yeah, got to start somewhere, and I respect having one definition of the bins and using that first. But interesting area to maybe do some more work in. Nathan, I see your hand. Go right ahead.
Yeah, maybe it's a stupid question, but this anomalous Zeeman effect, does it depend on the property, like the size of the magnetic region, or is it something that you expect to be fairly similar across magnetic regions, or do you have certain types which are more prone to it?
The anomalous pattern is a function of the line, really. So it'll be, it'll depend on what lines you're using. It should, if one plage is like another plage, you'll have the same scalings with wavelength and magnetic field strength and the area of your feature as Ansgar showed before. But individual lines are going to be different based on their particular anomalous pattern and its parameters.
Thanks.
Nuno Santos, go right ahead.
Yeah, hi, Steve. Very, very nice talk. Thank you very much. I have a very simple question because I'm not aware of the numbers, but so what are the typical G values for the lines, the iron lines in the sun? So here are doing it all for 1.5, give or take, but what is the typical values?
Typical value is like a little more than 1, not, around 1.1 or so. It really depends on your sample.
Okay, so then yeah, go on.
So this is a little bit more magnetic than typical.
Okay, so it's not everything is bad in that sense, right? So
it's not quite that bad, and it scales roughly like what scales, but like, I mean, we've been scaling all these things with G effective up till now, but clearly that's not enough. But at least to 0th order G effective still kind of works. It'll go like G effective squared. So that does help you out in average. And the other thing that helps you out in average is going back here, the distribution. Yeah. Okay. I computed these curves, these strength curves for a lot of different strength lines. But in fact, most of the lines that you use for RVs are not these ones that have the largest amplitudes, because those are the very weak ones. Most of them are in lower amplitude section, and that's why the weighted average comes out to be only around plus minus 11 for this. But when you say when one would point out that look, the fluctuations that we see on the sun, maybe with Hart's North, aren't plus or minus 11 meters per second. I think that might be partly because of the way we're measuring the radial velocities, is that we're with the CCF, you're kind of mashing all these together, and you're also doing this, doing a weighting by line depth, and that pushes you towards weighting it by the ones that really don't vary much less here, that are closer to 0. So that's an additional property. I think I could redo the calculation with an additional weighting on line depth and see how that would affect the net signal. That should be probably closer to what you observe on the sun with the current CCF methods.
okay, thank you.
Alejandro, go right ahead.
Hi, and thanks, Steve. It has been a very interesting talk. I have a question about, like, it's a bit on a continuation of what you just said. Right now, there are a bunch of line-by-line radial velocity methods, and I bet we're going to get a few more in the future, because you get quite a few useful properties in your data. How effective do you think working in this, at which level do you think it will be possible to correct this without like throwing away all the lines once you have like all the individual velocities?
Well, I mean, if you can figure out the right groupings and the right scalings, you may not be able have to throw out much, many lines at least. I mean, I guess you're still left with you know that you're doing things line by line rather than combining them. But I think doing things line by line or in small groups here is gonna really help. I don't know if that actually answers your question.
Okay, any other questions for Steve? Okay, if not, let's say thank you again for an excellent talk and an exciting new direction of research to pursue. And we will see folks, hopefully some of you at the Etalon community discussion on the 22nd. Again, that will go out in an email tomorrow with connection details and such. And then many of you hopefully in person in Santa Barbara later this month. So thanks everybody for calling in. Thank you again to Steve for an excellent presentation and catch you all soon.